This is Unit 1, the alphabet and grammar of geometry. Lesson 1.3, the grammar of geometry, part 2. Make sure you get the date, time, location, and a parent or guardian or teacher sign-off. Students, once again, focused attention equals faster work. Do not attempt to multitask while following along and interacting with this video. Taking a look here, I'd like you to try this page on your own, working in pencil. When you are finished, get out a red pen and be ready to correct your work. Welcome back. Let's see how you did here. Again, you should have done this on your own, and now you're checking your work. We're going to read the conditional, write its converse, inverse, contrapositive. If you sing daily, so the hypothesis there is sing daily, then you will have a happy heart. That is your conditional. The converse is something like if blah blah happy heart, then you sing daily. That would be the converse. Converse, you switch. Inverse, you flip the meanings. So if not sing daily, then not a happy heart. Contrapositive is switch and flip. So if not happy heart, then not sing daily. Obviously, I'm taking a little bit of liberty with the grammar there to simplify this. Number 2, many of you thought you got number 2 wrong, but you didn't. I'll explain why many of you thought you were wrong here. We cross multiply. Whenever you cross multiply, I never want you to distribute in your head. Notice I didn't instantly multiply that 3 out. I prefer you to simply write everything down first, then do your distributive or your multiplying. So many of you got to this point and you asked yourself, am I wrong? And the reason why you asked yourself this question is because the answer is a fraction. Students, get this real clear right now. This is a math class. Fractions are a number. Numbers are allowed in a math class. So please don't ever ask me if your question is right or wrong simply on the basis that it's a fraction. Fractions are always possible. Fractions are numbers. We are in a math class. Numbers are acceptable. So you can leave that improper, or some of you might have changed it to a mixed fraction. 3 goes in there approximately 4 times. That's 12 with 2 leftovers. That's 2/3. Some of you might have changed it to a decimal, 4.66 repeating, folks. You were not wrong. On that very important note, we're going to continue our study of the grammar of geometry using inductive and deductive reasoning. Key terms: inductive, deductive, law of syllogism. Read these aloud with me. Law of detachment, law of contrapositive, conjunction, disjunction. like you to take a moment, just 10 seconds, and I'd like you to carefully observe every single picture of these professional golfers. Just take a quick glance at them for 10 seconds. Couple observations. In every single one of these pictures, these professional golfers possessed a golf club. And another thing you noticed is as they are golfing, all of them are wearing a hat of some sort to keep the glare off their eyes. So if you were, a couple things you should notice is that they all have golf clubs and hats. Now, I'd like you to read this with me out loud. Imagine that you knew absolutely nothing about professional golf attire. To learn more, you decide to attend all professional golf matches in a year, and you observe, underline that word observe, very closely each golfer's outfit. After observing hundreds, underline those two words, of professional golfers on the course, you conclude that if, underline the word conclude, that if someone is a professional golfer, then he or she always wears a hat on the course. Therefore, you come to the general conclusion that all professional golfers wear hats on a course. This logic process is called inductive reasoning. Let me explain the difference between inductive and deductive reasoning. Okay, to clarify, if you go through a process of making many observations, like you did going and watching hundreds and hundreds of professional golfers, and you have what's called an aha moment, oh, I got it. You come to a general truth. If you're a golfer, you wear a hat on a course. So if you discover a general truth, that is inductive reasoning. Then if you take the general truth and you apply it to a specific situation, that's called deductive reasoning. So inductive, you discover truth. Deductive, you use truth. Let me give you a couple more examples. Let's go back to our golfer example. Okay, so on this page, you used inductive reasoning after hundreds of observations to come to the general conclusion that All professional golfers wear hats on the course. That's inductive reasoning. Now let me paint another scenario. Now back to the golf example. After multiple observations, you come to the conclusion, notice that word conclusion, that all professional golfers wear hats on the competition course. That was a discovered truth. So write the word truth here. Now let's say you meet a Mr. Tin Vu at a restaurant, and he tells you he's a professional golfer. He's sitting in a restaurant and he's in a full suit and tie. What assumption can you make about his choice of clothing when he's on the golfing green? And if you were to envision that on the golfing green, we would have a Mr. Tin Vu in a hat. It's a very bad rendition. Sorry, art students, I'm doing my best there. Then that is called deductive reasoning. So the deduction would be Mr. Tin Vu wears a hat on the golf course. Why? Because we applied it specifically to a specific situation. So inductive reasoning, you discover truth. Deductive reasoning, you apply truth to a specific situation. What I'd like you to do on this page is read these two different scenarios to yourself out loud, underlining key words. Then determine whether they're inductive or deductive reasoning. Pause the video. Welcome back. Keywords here in the Olympic athlete, it says you know that all athletes, so that is a given truth. And then you applied it to a specific situation. So that is an example of deductive reasoning. Down here, we tested a hypothesis, hundreds of experiments, and then you come to a general conclusion. This was an example of inductive reasoning. Now, along with inductive and deductive reasoning, we're going to learn three different logic laws. Now, don't be put off by these fancy names or fancy symbols. You're honestly surrounded by this logic every day at school and in home life. I'll give you an example of each of them. So the three laws are the law of contrapositive, the law of detachment, and the law of syllogism. I'm going to be teaching you symbols for these laws. Now, these symbols, don't be overwhelmed by how fancy you are. Remember back in 6th, 7th, or 8th grade, whenever you took pre-algebra, and we started taking things like this, 3 plus an unknown equals 7. And then instead of making a blank for an unknown, like you did maybe in 2nd or 3rd grade, we started doing this. 3 plus x equals 7. So we used a variable. Now, some question might have crossed your mind, why do we use x? Don't know. Some mathematician centuries ago decided to use x. Maybe it was easy to write in that language. Who knows? But x became the standard variable for basic unknowns. Of course, any lowercase cursive letter in algebraic equations stand for unknowns, but we use x. So I'm going to be using the symbols of, just put them in the margin so you're familiar with them, P, Q, and R. Now, just like X in algebra is actually a replacement for number values, P, Q, and R are just shortcut replacements for statements. So don't be put off. Why P, Q, and R? No clue. Someone decided P, Q, and R. They all go in the alphabet next to each other. They're easy to write, but they are the variables that we are going to use to replace statements to make things shorter and easier to see. So law of contrapositive, you saw this a little bit the last time. You start with a conditional. If you drive a Mini, then you drive a car. And that is a true statement. If you're driving a Mini, you're driving a car. So just write the word true here. And we're going to use the symbols like this. The premise of drive a Mini, we're going to say is P. Then we replace with an arrow. You drive a car, Q. If you drive a Mini, then you drive a car. Well, we know that the converse, if you drive a car, then you drive a Mini, that's not true. I could be driving a Volkswagen. So of the three variants, converse, inverse, and contrapositive, only the contrapositive is forced to be true. The contrapositive would look like this. If you don't drive a car, then you don't drive a Mini. That's the contrapositive, the switch and negate. That is a true statement. If you're not driving a car, you cannot be driving a British Mini. And it looks like this in symbols. Remember, the car was the Q statement. So to say opposite of Q, we go like this. Opposite of Q. Opposite of P. That little, what looks like a Spanish tilde, for those of you in Spanish, that is the symbol we use in geometry to represent opposite. So in complete symbology, the law of contrapositive says this. If P then Q is true, or a conditional is true, therefore, these three little dots mean therefore, a logical conclusion that you can make is the contrapositive is also true. That's called the law of contrapositive. If a conditional is true, the contrapositive is the only one forced to be true. Converse and inverse are like babies. Don't know for sure. Contrapositive. Law of detachment, a very fancy thing for something we just did using inductive and deductive reasoning. You start with a generalization. For example, if you own a car, then you can drive yourself to work. By deductive reasoning, you apply it to a specific situation. If Aman owns a car, then the logical conclusion is Aman can drive himself to work. We have a general conditional that's true. You apply it to a specific situation that is also true. If you own a car, then you can drive yourself to work. General truth. If a mon owns a car, then a mon can drive himself to work. That's called law of detachment. Symbols look like this. If if general, P then Q is true. A general condition is true. And P true in a specific situation. In this case, it was a mon. Conclusion, the application is true. Q true. If a general P then Q is true and a specific P is true, the specific Q is true. It's called law of detachment, folks. Law of syllogism. You are swimming in this practically every day, especially people in authority in your life. You might hear something like this from your parents. If you clean your room this Friday, then you can get the family car. If you get the family car, then you can go out with your friends. Conclusion, if you clean your room, then you can go out with your friends. That is a syllogism. You hear it all the time from coaches and parents and teachers. Next time you hear it, toss back and say, hey, that was a syllogism. Nice fancy word. Ready? We're going to use the symbols. If you get a job, that's going to be our P statement. Then you can earn money. That's our Q statement. If you earn money, that's our Q statement again. Then you can purchase a car. We're going to add a third variable because that's a third statement. Conclusion. If you get a job, then you can purchase a car. That is the law of syllogism. It looks like this in symbols. If P and Q is true and Q then R is true, conclusion, if P then R is true. That's a law of syllogism. You're going to write the logical conclusion of the statement, and then you're going to write the logic law that it demonstrates. We're going to do this together. If you practice math daily, then your math skills will improve. If your math skills improve, then you will do well on math tests. You should recognize that this is a syllogism. Practice daily, improve. Improve is our Q statement. Math tests is the R. Conclusion is if practice math daily, if you practice math daily, then you will improve on math tests. That was an if P, then R statement. That is a law of syllogism. Let's try this page together here. It says, if you learn a new language, then you will have more interconnected neurons. If you have more interconnected neurons, then you're smarter. You should recognize this as a syllogism. New language, interconnected neurons. Interconnected neurons, smarter. Conclusion is, if you learn a new language, then you're smarter in the sense of a more efficient brain functioning. The logic law there is law of syllogism. If someone is a medical doctor, then they took a full year of anatomy and physiology in college. Monica is a medical doctor. Notice what we did here. We had a general, someone, anybody, medical doctor, took a year of A&P in university. Anatomy and physiology is called A&P at the university level. Monica is a medical doctor. That's a specific P. So the conclusion is the specific Q. Monica took a full year of A&P in college. The logic law there is law of detachment. You're going to try this page completely on your own, then switch to a red pen and correct. Pause the video, do this on your own. Welcome back. You should have a red pen in hand. Taking a look here. If you are a Valley Theater major, then you must participate in at least one Valley Theater production. Marcus is a Valley Theater major. Conclusion is Marcus will Valley Theater production. This was law of detachment. If you pray daily, Then you connect with God's love consistently. If you connect with God's love, then it will be easier to love others. This obviously is a syllogism. If you pray daily, then easier to love others. And of course, that is a law of syllogism. Go ahead now. You're going to take 2 minutes and flip back through every page. Review the new vocabulary and the meaning of the new vocabulary. Do this talking to yourself or get yourself an audience, but do rehearse this verbally on your own. Lesson 1.3.